Hello everyone and welcome back. Today we're going to talk about estimations using Taylor series. Now, Taylor series are generally centered at A, but just to introduce the concept without putting too many characters up on the screen, I'm looking at a Taylor series centered at 0 right now in order to come up with the concept here. Any Taylor series representing a function is going to be a power series that goes on forever. No worries, David. I know everybody's, there's a lot of stuff going on. I'm glad to see you're here. We're good. Okay? Yeah. Now, the Taylor series that is coming through, I can break up into two pieces in order to do estimations. I'm going to grab the first little chunk, and I can make different size chunks. This one here is a chunk that I picked out just to grab stopping at the second power. That represents these three terms added together represents the second order approximation, the second partial series. Those three terms is the second partial series, which I label T sub 2, the second Taylor series. It involves all the Taylor series up to power 2. Now, if I stop at power 2, that means all the bigger, what did I write there? That means that all the rest of the terms I'm ignoring. From the third term, the fourth term, the fifth term, the sixth term. I'm ignoring all those by looking at the second power series. If I add up all the rest of the terms, I'm going to have a remainder. And so the original function is going to be given by the Taylor series inside the interval of convergence. And that original function can be represented as the second or third or fourth or nth polynomial Taylor partial series, which is going to be my estimation, plus everything else, which I then call the nth remainder. The nth remainder starts with the next term after n. So the second remainder starts at the third power. The second Taylor ends at the second power. The second remainder starts at the third power and then goes on forever. Now, the good news is this second power, the second remainder, is actually equal to this third term, ignoring everything else, if I pick the right value of x in that interval. The entire remainder is going to be equal to just the third term if I pick the right value. This is a consequence of the intermediate value theorem. The actual proof is kind of convoluted. It's in the text in section 6.3. It involves introducing a kind of ingenious function that I just don't really have time to go over with you guys in detail, if I'm also going to be able to go into examples in detail. Okay, reminding everyone, if my audio starts chopping, please pick up your hand so that I can know that there's something wrong, because I'm not going to see it or hear it from here. Okay, so there's the idea here. The function, which is equal to its Taylor series inside the interval, is going to be equal to approximation plus a remainder, and the remainder we can judge by the third term. Now the idea is that the remainder, the whole thing, is actually equal to the third term at a particular value for x. At a particular value of x, this third term, this c sub 3, this 3 x cubed term, is going to be equal to everything that goes on after it. And so the idea is, I know if I have a maximum value for this third term, then I will know that the second order approximation is accurate to within that maximum value for this third term. And now we're going to look at that as an official theorem. That's what you want to think of, though. I'm going to approximate going up to some particular power, the second power, the third power, the fifth power, the nth power. And then I'm going to know the answer is correct if to within what the very next term is if I pick the right value. So in particular, if I know what the largest possible value for this is inside my interval, then I will know that my approximation is correct to within that amount of error. The idea is I want to do this correctly so that I know the largest possible value of this next term is like 1 in 1,000, is less than 1,000. And that would guarantee I'm correct to 3 decimal places. So let's look at the theorem. The theorem says if I'm giving the nth remainder, remember this is the sum starting with the n plus first power, which involves the n plus first derivative at a divided by n plus 1 factorial. In either case, notice we had here the function is equal to the second partial series plus the second remainder, which is everything else. And so the second remainder is equal to the function minus its second Taylor series. That's what the theorem starts off with. The remainder, the nth remainder, is equal to the function minus the nth Taylor. The nth Taylor is the sum all the way up to the x to the n power, or x minus a to the n. The nth remainder starts where the nth Taylor partial series leaves off. So it starts at the n plus first derivative and keeps on going. In the example above, it would start off with the third derivative at a over 3 factorial. And the idea here is, for the remainder on some interval of convergence that includes a value a, I am guaranteed by this theorem that there is a value c between the a where I'm expanding and the x value where I'm trying to look at in the interval, so that I can actually find the remainder is actually equal to the n plus first derivative. This is the n plus 1 term, the one dealing with the n plus 1 power, at some value c. Now, if it's equal to, this is c sub n plus 1 here, at c, not at a, not at x, but it's some value between a and the x that I'm trying to approximate. In just a moment, x will be 11, and a 8, and the function will be the cube root function. That's the one I'm going to be working with. So the n plus first derivative at some value c between the that you're expanding around and the x that you're trying to evaluate, divided by n plus 1 factorial. So that means that if I can know what I don't know what the c is, I don't know what that c is, I'm not going to be able to find that c. But the fact that that c exists tells me that if this nth derivative at any particular value is less than some value m, say, an absolute value, for any x level, then the remainder is to be less than that nth derivative plus first derivative of x divided by n plus 1 factorial. X minus a to the n plus 1. This is the idea, is we've just found a limit on that coefficient. All right, so let's put that into reality for you guys with an example. we're going to approximate the cube root of 11 using the cube root of x near 8. So a is going to be 8 in the example, and we're going to approximate the cube root of 11 here. So let's get started. Okay? So we have the idea here, right? What's the function that we're working with? You can tell me what function I'm working with. What function am I working with, guys? Somebody tell me in the chat. Anybody? What function am I working with here? It's actually written. What is it? Yeah, I need people to follow along with this. It's really, really important. Yes, it's the cube root function. So we're looking at x to the 1/3 for n equals 0. The 0th derivative is x to the 1/3, right? Okay. And we're going to be approximating this, okay, near 8, yes? Okay. And so now I want a is 8. I want the nth derivative evaluated at 8. What's that? What's the nth derivative evaluated at 8, guys? 2. Lourdes is with me. Do people know what she's doing? Yeah, thank you, Deborah. Thank you, Kayleen. Yeah, this is really, really important if this is going to work for you guys. Thank you. Man, this is so difficult without being able to see your faces. And that's why I need feedback all the time. Thank you, guys. 2. And so we actually like that 0th term. It's just, yeah, that's like 0 right here. Except we have to divide by 0 factorial. This factorial is 1. And so the Taylor's starting out with 2. Right? Okay. Now, here we go to the first derivative. What's the derivative of this thing, guys? What's the first derivative? What's the derivative of x to the 1/3? What's the derivative of x to the 1/3, guys? Anybody? 1/3 x to the negative 2/3. 1/3 x to the negative 2/3. What is that derivative at 8? Plug in 8. What do you get on this, guys? What do you get when you plug in 8 on that? What do you get when you plug in 8 on this, guys? Lourdes is very fast. Lourdes is very fast. Guess that? Yeah. This right here, I'm putting in 8. I'm going to just kind of in a different color so you can see it. 8. This is 1 over 3 to the 2/3. Yes. 8 is 1 over 3, 8 to the 2/3. And that's 1 over 3 times 8 to the 1/3 squared. And it's 1 over 3 times 2 squared. And what everybody here is saying 1/12. That was very good arithmetic from the guys to be able to set, but there it is, right? So there it is, it's 1/12. Awesome. Now, second derivative. Second derivative. N is 2 now. What's the second derivative, guys? What's the second derivative? Negative 2/9 x to the negative 5/3. Yes? Okay, now, my next question is, What is the second derivative evaluated at 8? What is the second derivative evaluated at 8? Yeah, this one you're going to have to work out for a bit, okay? 9 times 16 is 144. That's right. Check your sign. Check your sign, Lourdes. There you go. -1. But she got the arithmetic. Yeah, right. Okay, the sign. -1 over 144. So 8 to the 1/3 is 2. 2 to the 5th is 32. 2 to the -5th, 32 to the is 32 to the -1 is 1 over 32. So I'm looking at -1 over 16 times 9. 9 times 16, 140. You did great. You did great. Okay. Yeah. And so the number is now -1 over 144. Okay. Do I want to do another power? I don't think so. Well, I have to do another power for something else for the estimation. So let's do the estimation too. Let me give myself just a tiny little bit more real estate. That's a whole lot more real estate. Let's just kind of do it here. There we go. Now let's find the third derivative. What's the third derivative on this, guys? What's the third derivative? And people are ready on this one. Cool. So I'm seeing positive 10 27ths times x to the negative 8/3, right? -8/3. Okay. So this one right there, okay. We're going to worry about that just a little bit right now. Okay. But right now what I want to do is I want to find the second Taylor series, okay? T2 of x centered at 8. T2 of x, yeah, that's fine. To the -8/3. Oh, I didn't even see her arithmetic. I didn't even see the signer in there. That's right. Thank you, Lourdes. Yeah, yeah, that's cool. Don't worry about the x. Put it in there. That's great, David, Ryan. Yeah, okay. Yeah, and that was great. That was great. Okay. And now T2 of x, guys. So let's write T2 of x. What is C sub 0 here, guys? What is C sub 0? Somebody tell me for T2 of x, we're centering at 8. What's T2? 2. Very good. 2 plus. What is C sub 1? What is C sub 1, guys? What is C sub 1? 1/12. Okay. And now, what am I taking powers of? What am I taking powers of? Remember, I'm centering at 8. What am I taking powers of? I opened a parenthesis here. What am I going to put in that parenthesis? What am I taking powers of? I'm centering at 8, guys. X minus 8. Thank you, Kayleen. X minus 8. In just a second, X is going to become 11. Okay? X minus 8. X minus 8, Anthony, right? Okay? Now, what is C sub 2? What's the second coefficient? What's the second coefficient, guys? What's the second coefficient? Everybody's tossing numbers in. That's really nice. We're kind of getting there here. You got the sign right this time. You know what you forgot, Lourdes? Think about it for a second. What did you forget? Everybody's got kind of an idea on this. Great. But you all forgot something. What are you forgetting? Think about it. Think about it. What are you forgetting? Is the second over the factorial. There you go. And I wanted you guys to run into that error because it's so freaking common. People always forget the factorial, right? So over here on the top right here, I'm going to do this. Fn of 8 over n factorial. See? There we go. That doesn't make a difference for the first one because 0 factorial is 1. Doesn't make a difference for C1 because 1 factorial is 1. This time, though, because I'm dealing with a second factorial and 2 factorial is 2, this makes my C2 negative 1 over 288. Okay, that was a really important error to make, and so I tried to force everyone into that error by leaving out that that last column. Okay, and so the second coefficient, as everyone is understanding now, is negative 1 over 288. What am I going to take a power of, guys? It's x. What am I plugging into the parentheses now? And remember, x is about to become 11. X is about to become 11. Okay? So what do we got here? Yeah. What do we got here? X minus 8 squared. Thank you, Kayleen. That's perfect. Okay? And it's going to be, that's just the second partial series, right? And that's the second power series. I've gotten up to the second power. That is the second partial series. Okay? Now, we're going to plug in 11 to get an approximation for the cube root of 11. Everybody needs to have calculators too, guys, because we're going to come up with decimal approximations on this stuff. 2 plus 11 minus 8 over 12, right? That's 3/12, yes? That's 3/12, right? Plus negative, or should I say minus 11 minus 8 squared over 288, yes? Okay, the first one is 3 over 8, right? 3 over 12, I'm sorry, that's 1/4, isn't it? And this last one is 9 over 288. 9 over 288, yes? And remember that the 288 was 1 over 32. Very good. Negative 1 over 32. And that's negative 1 over 32 now. Right? Okay. And so what do we got here? 2 plus 1/4 minus 31 over 32. Right? I'm just going to go ahead because this one works out nice in fractions, right? Make sure I agree here. Yes, 16/2 is 32. Very good. Thank you, Lourdes. Okay. 32, right? 32. That's 64, 65, 64 30 seconds, 65 30, no, 64. I'm running out of room. I'm at the bottom of my screen. 64 plus 8 minus 1 over 32, 71 30 seconds. Okay, somebody give me an approximation on that. Yes, that's right. 64 plus 8 minus 1. 71 30 seconds. let me get a calculator on this. What's the calculator on this, guys? Where's my calculator? Oh, here's my bag. Okay, and I'm going to check you guys. That's good. 71 divide 32. And the answer is 2.218725, right? And that's an exact because it's a power of 2 on the bottom. 2.21875. And now, guys, what's the cube root of 11? What's the cube root of 11? What's the cube root of 11, guys? 2.22398. And it goes on going, right? I ran out of room at the bottom of the screen. That's like a cardinal sin. 2.223, etc., right? So, yeah, 98, yeah, whatever. But I just wanted to see right here. This is as close as we got. 2.21, 2.22. So we were within. What's the difference between those two? The answer is the difference right there, the error, the actual error. And now that I ran out of room, it's really awful that I have to write back up. The error is 0.005. 0.005. I actually subtracted the one from the other. Yeah? Okay. So the error there, and I will clean this up before I put it up online on the notes. Can't do anything about the video, but there it is. The error here is actually 0.00523, etc. 0.00523, etc. Okay. Now that error, guys, is 0.005, right? Yeah. And I want to point out, guys, what is 3 factorial? 3 factorial is what? 3 factorial? I can't do it. I've run out of room for this. I should have pushed this example way up higher on the page so I'd have more room, but I didn't want that to show up. When I rewrite this for the notes here, I'm going to rewrite this starting with the estimate up here, and then I'll finish the rest of that down here. But that's enough, guys. So we came up with an approximation using the second power right there, and it was already there within 0.005 by the time we got to the second Taylor partial series. Pretty cool, huh? Okay, so let's just go to a different example. This time I'm going to square root of 10. We're going to try to estimate the square root of 10, and this is going to go on for a while. Okay, I'm going to approximate this at a equals 9, and I want to take it up to the third order approximation, and then I want to show that approximation is less than 1 over 1,000. Okay, we're going to show that 2 ways. We're going to show it first of all just by using a calculator to show that our approximation is less than 1 in 1,000. And then we're going to use the theory to show that that third remainder was less than 1,000. Okay? So here we go, guys. What function am I going to use on this one, guys? What's the function here? What's the function I want to use here? Yes, x to the 1/2. So my function is square root x, or x to the 1/2. Okay? And this is for n equals 0. The 0th derivative is the original function. Okay? And now, let me get myself framed here because I want to go to n equals 3, right? So that means I want to look at the fourth derivative by the time I'm done. So there I am, okay? So what's the first derivative here, guys? What's the first derivative? First derivative? First derivative, guys. We can do this. What's the first derivative? That's right. It's 1/2 x to the negative 1/2. Okay, there we go. Thank you, Ryan. Thank you, Timothy. Thank you, Anthony. There we go. Okay, so I'm happy that everyone is with me, and also obviously people are hearing me. We're not getting big up breakups like I had yesterday. Okay, what's the second derivative? What's the second derivative? We're going to be evaluating this at 9. We're going to evaluate it at 9 because I want the square root of 10. Let me reframe it so you can actually see the problem that we're working. There we go. We're going to be looking at the square root of 10, and we're going to start out with approximation at the square root of 9 and kind of go from there. Yeah. Now, the next derivative, as I'm seeing right there, is 1/4 x to the negative 3/2. Okay? No, that's the number of the derivative, because I started out 0, because I started with the 0th derivative is the original function. Okay, that's the idea. And then the 1 that you're seeing for n is now that, and you're confusing the n's with a's, okay. The 1 is going to be the first derivative, and that's going to lead to the first Taylor. Okay, that's a negative 1/4, thank you. Okay, and now what's the third derivative, guys? This is where we're going to come up with approximation, right? And this is where the approximation is going to end, but the remainder is going to start at 4. And so this could be negative 3/8, positive 3/8, x to the negative 5/2. Okay? And now I'm also going to need the fourth derivative for the estimates. And for what's the fourth derivative? No worries. Not like I don't like make plenty of arithmetic errors myself in here. Okay. And so what's the next derivative, guys? Looks like negative 15/16. Yeah, negative 15/16. X to the negative 7/2. Now you can see from the problem here, we're approximating the square root of 10 by starting at the square root of 9. Okay? And now we're going to want to evaluate all of these things at 9. Okay? At 9. So, let's do the first one. What's C0 here? What's the 9? What's 9 at here? Plugging in 9 into x to the 1/2. What do you get? 3? That's easy, right? That was the whole idea. Okay? Thank you, Deborah. That's awesome. That one's way easy. Everybody should see that one. Now, let's go to the next one. What's the first derivative at 9? Number 2 is 1. Very good. 1/6. Okay? And that's also C1, because we're still in the 0 factorial, 1 factorial, everything is equal to 1. Okay. And now, what is the second derivative at 9? Thank you, Anthony. That's awesome. What's the second derivative at 9 now? And people are working on this one. That looks good. 4 times 27, 54, 108. Yes, negative 1 over 108. Anthony's just like rocking and rolling here. That's great. Negative 1 over 108. Everybody's getting that? Okay. Right. And on this next one that kind of ends our approximations, yeah, that's good. I'm going to wait for everybody to get me the next one too then, okay? And I'm going to do some calculation myself here. The next one, I got what? Looks like I'm getting 3 to the 5th in the denominator. It's going to put 3 to the 4th. I'm seeing 80. 3 to the 4th is 81. Okay, but 3 to the 4th is 81. 81 times 8. 81 times 8. 648. That's what I'm getting to. 648. 1 over 648, yeah? Okay. Now, I'm going to give you guys a little fast trick. Number 4 is, yeah, we're not actually going to do, we're number 4 right there. I'm not going to actually plug it in at 9, other than the sense that I'm interested in knowing, how do I want to put this? This is an alternating series, guys. With an alternating series, the error in any particular partial series is always less than the absolute value of the next term. Yeah, which is pretty cool. And in that sense right there, yeah, Ryan's thing has to, but I haven't done that theory yet, so we're not going to talk about that. Okay. Anyway, so here we go, guys. And now, let's go ahead and do the C sub n's, okay? That means we're going to divide by n factorial. The nth derivative, and let me write that neatly, at 9 over n factorial, and I might remind you guys that's the nth coefficient, okay? So what's C0, guys? What's C0? Everybody read C0, just read it off for me. C0, please. 3. Okay. C1, yeah, C0 is really easy. Yeah. What's 1? Okay. And Deborah, that was kind of weird. Okay. And we're actually doing this expanding at 9, Deborah. If you look at the power series, it'd be 16x minus 9 to the first over 1 factorial. Okay? Yeah. And yeah, so the next term is 1/6. Very good. C1 is 1/6. C2 now. What's C2? Yeah. C2 is negative 1 over 216. Okay. What's C3, guys? What's C3, guys? What's C3? That's what I is. It's times 6, Kayleen, times 6. 3 factorial is 6. Yeah. What did you do? 1296? Oh, your time it was C3 is times 3 factorial. Yeah, okay. And just getting that, that's 1 over 38, 88. Okay? There we go. Okay. So let's get ourselves some space here to take a look at what we've got, right? So now what I have here is that the function itself, root x, okay? Get just enough room to write this, so I'm ready to do this, okay? Root x is equal to C0, 3, plus C1 at 9 over 6, yes? Okay. Plus the second power, except that's a negative. Second power over 216 plus the third power over 3888. Okay. And now, do I want to do it for the fourth power or not? Yes. There it is. Okay. And I'm going to go do the fourth power now too as well. I'm going to plug in what's the fourth derivative at 9. That's why we did this, because it's going to come up with some nice, easy number. The fourth derivative at 9. Fourth derivative at 9 has the numbers in it. Okay. The fourth derivative at 9, I need 3 to the 7th power, 3 to the 6th power, 3 to the 6th power, and that's not to take care of the 5. So I know what, -5, I'll rewrite this in blue in a second. 3 to the 6th power times 16 is 11664. Yeah, that's what it is. Yeah. Over 1164. Right. -5 over 1164. Okay. Lourdes, check my numbers on that, okay? And then 4 fail. Whoa. Okay. And I take that times factorial and I get this huge thing. -5 over 279,936. Yay. Ah, ha, ha, ha. Minus 5, x minus 9th, x minus 9 to the 4th over 279,936. Yeah, plus things. I want to point out, guys, that at this point, after we've passed the first two in here, after the first two, everything is alternating, which is useful. Now we are to try our approximation for root 10. Equals 3 plus 1/6 minus 1/260. 1 over 3888 minus 5 over 279,936 plus ... Okay? Now, one advantages of the alternating series, yeah, the advantages of the alternating series, I'll check that in just a second, right? Is that this T3 and this R3 and this is happening at 11, right? I know the remainder R3, okay? The remainder is going to be less than this term, okay? The remainder is going to be less than this term. In general, inside the interval, and I can make the interval just ending up at 11, at 10, right? Yeah. In this interval, yeah. This value, this, I'm looking for the maximum value of this term in this interval. And the maximum value of that particular term is going to be a 10 in this interval. Or so close to 10 doesn't matter. So let's go ahead and do the thing though right now, okay? I'm doing the thing, and let's go ahead and calculate T3 at 11. Okay, then now we're just going to go ahead and plug this thing in right there and find out what T3 at 11 was. 3, and I'm just going to work with a decimal approximation. 3 plus 1/6 minus 1 over 216 plus 1 over 3888. And that is, okay, I'm off somewhere. Oh, I see what happened. You added the next term. Okay. The T3 approximation, according to my calculator, the T3 approximation is a number really close to 3.16229. Okay? Now, what's the actual square root of 11? What's the actual square root of 11, guys? I'm sorry, 10. I'm sorry. I got confused between this problem and the last problem, didn't I? So I took the cube root of 11, but now I'm taking the square root of 10. What's the square root of 10? And I wrote 11 again, didn't I? 10, the square root of 10 is, push the SD button on your calculator. I know which calculator it is, and so I know you need to punch the SD button. Yeah. And yeah. You guys are all using the Casios, right? Yeah, I thought it was funny too. But I get students up in the early, they say, "Oh no, how do I get a decimal approximation of this thing?" And because I don't use Casios, I had to have a student tell me. And the answer is use the SD button. I don't even know what SD stands for. I just know you punch that and you get the decimals. Yep. Okay, so root 10. I'm seeing 10 to the 0.5 is 3.16227. Yes? Okay, this one right, because I want to know how far my estimate is off. Yeah. And I'm going to show in just a sec. Let's go ahead and do this, okay? How far was my actual error? What was my actual error? My error is the difference between those two. So here's my actual error. And I think you're chopping a little bit on that one. But here's the error that I come up with. 0, 0, 0. And I'm generally interested in the absolute value of the error. So you take whichever it is and you subtract, and whether it's negative or positive, and just treat it like a positive. I get 4 zeros followed by 1, 6, 5, 7, 9. Okay? And now I want to take a look at T4 at 11, at R4 at 11. I'm saying that R4 at 11 is going to be less than this next term, this 5 over 200 and whatever thing. Okay? And, criminy, I'm at the bottom of the page again. And 5 over 279936. Criminy, I'm wrong place. Oh, criminy, that's 10:01 and I'm in the middle of this class. Okay, yeah. 5 over, what is it? What did I just say? 279936? Equals. What's this thing, guys? Okay, I just wanted to see the numbers separately, right? Okay, what's this thing? 5 over 279936. I just got an urgent email from Nikki. 0.000017,861. And here is the point, guys. The actual error is less than the value of the next term. That's the important thing. Now let me go ahead and see if I can't take care of this fire from Nikki. I'm not gonna pause the recording, but let you guys take a look at that for just a second. Okay. Okay, we need Patricia and Joshua to contact Carla immediately for their laptops. This is the fire that I've got to take care of because they're trying to deliver laptops, home deliveries on laptops right now. And so I need to send an email to these two guys. Forward. Forward. Okay. Patricia. Let's see if Patricia's in there. Yes, I've got an email from Patricia. Okay, and now the other one is Joshua. Do I have? Yes, I have email for Joshua. Now, now, now. And copy core. Now, now, now. Sent. That's what I can do. Okay. And hopefully that will do. Okay, I don't want to talk about that too much. Okay, I'm back to Chrome. I'm back to you guys. Sorry about that. Ooh, more of the fires I need to put out right now. Okay. The point on this exercise here again, okay, was to show you guys that the actual error was less than the next term's maximum value. And this particular case, the maximum value for the next term was at 10 in this interval, when x was 10 at the interval, which gave me a value of negative 5 over 279,936, which we can see was actually bigger than the original error. So that's pretty cool, huh? So at T3 of x, we were able to come up with an approximation, which is just a fraction, something we can calculate. This, whatever this is, it looks kind of way too big fractions, right? But yeah, you could do this by hand if you did if you needed to come up with an approximation for the square. And I kept on writing 11 when I needed to write 10 because I was distracted. There we go. Okay. And this was the fourth term on there. So let's undo this right there and show you this is what we did this time, okay? So let's go over the steps here. And the steps involved identifying the function and identifying the place, the a value that we're going to expand around, okay? And now we take the function and we take derivatives until we're happy. And we evaluate the derivatives, including the original function, which is the 0th derivative, at the value where we're expanding. And then we divide by the factorial to get the coefficients. Then we develop the Taylor series as far as we're going to use it for estimation. This is the third order estimation, which involves 4 numbers, ending in the third power. And those 4 numbers added together gave me an approximation using the Taylor series that was within 0.00016, which was less than the next term's maximum value of 5279936, which was equal to 0.000017861. Whew! We have 9 minutes. That is not real. That's the one that's real. It's going to be lower than the maximum value of the n plus first term. That will often be, especially when it's an alternating series, that will always be the n plus 1 first term at that number that we're approximating. In general, it might be something in between, but especially with the alternating series, which are the favorite, everybody's favorite, which happens most often, that's all we have to look at. Okay? Yeah. So that's how that works. This time we're going to estimate E to within 1 over 1,000, okay? So this time I'm just going to straight out, because I've only got to, I have to blow through that other example. I am going to write the estimation, and this one we're going to estimate this at expanding around 0, so everything's easy, okay? So here is the series, and you can use the series, any series, if you get the Taylor series, you can use any Taylor series. You can pull it out of your memory if you want to. But any place you get the Taylor series from, it's a valid Taylor series. That's good. We'll just use it. And here the Taylor series for this is 1 plus x squared, and here I'm expanding around. This is the Maclaurin series for it. X squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus x to the 7th over 7 factorial. At this point, I think my factorials are bigger than 1,000. And so I'm happy. Okay? Now, let's go ahead and figure out what these were, okay? I want T0 at 1, because I'm going to approximate E. And everybody understands that E is just what happens when I plug in 1. Plug in 0 for x here. I'm sorry, plug in 1 for x here, and there it is. So what's T0 of 1, guys? These are my approximations for E. Maybe I should write that explicitly. E is approximately T0 of 1. What's T0 of 1, guys? 1. It's I could come up, that's my 0th order approximation, my initial approximation. What's my first order approximation? What's T1 of 1? Folks, what's T1 of 1? That's the first two terms added at 1. That's exactly the way it works, Lourdes. That's exactly the way it works. The first order approximation is going to be better than the 0th order approximation. The second order approximation is better. The third order approximation is better than the second. All the way through. Yes. What's T1 of 1, guys? What's T1 of 1? 2. Great. What's T2 of 1, guys? What's T2 of 1? And I don't want to get this all. What's T2 of 1? T2 of 1, guys. And now you start giving me decimal approximations is fine. T2 of 1, and what I'm doing here is I'm saying 1 plus, clear, 1 plus 1 plus 2 factorial, 2 to the negative 1. 2 inverse. On my calculator, I'm getting 2.5. I'm getting 2.5. For the second T2, this right here is 1 plus 1 plus 1 over 2 factorial, which is 1/2. Yep, I understand. And you're ahead of me, that's okay. I don't mind that. T3 of 1. For T3 of 1, I'm going to start with T2, and then I'm going to add, I'm going to start with T2, 1 plus 1 plus 1 over 2 factorial, and then I'm going to add 1 over 3 factorial, where I recognize 3 factorial is 6. Okay? And this right here was just 2 plus 1/2. And this one was 2.5 plus 1/6. And that's what I'm doing, okay? So it's 2.66s repeating. Very good. 2.6s. That's fine. Now let me get myself bigger. Okay? And now let's ask for the next one. T4 of x. T4 of 1. T4 of 1 is what? And I'll point out, guys, that 4 factorial is 24. 5 factorial is 120. 720. And then 5040. And that's why I knew that one was going to be within 1 over 1,000. So T4 of 1 is 2.708, threes repeating, right? Plus, where is that? T4, right? 24 inverse. I need to run this with my calculator to make sure I'm there. Yeah. This is 2.708 threes repeating. Okay. And now T5 of 1 is, I'm going to add to the last one, 1 over 120. 2.716s. Yes? I get 2.716s repeating. One over 24, I get 2.716s repeating. Is that what you're getting, Lourdes? I'm not sure what the 0.02257 is, but okay. Yeah, because we know that these things are always coming up with a 2, 2.5, 2.7, there'll be 2.71s, and then I'll get 2.718s. T6 of 1, I'm kind of running toward the end of time. T6 of 1, I need now to add 1 over 720 to this. And that gives me 2.71805s repeating. T5's repeating, and then T7 of 1. Yeah, but at this point I know I'm good. Okay, I happen to know. Okay, yeah, and in this interval, yeah. 1/7 factorial R7. Okay, R7, guys, I want to point out R7 for this interval. I think I'm going to finish this because I'm past time right now. Okay, so there's T6 at 1. Okay. And I'm going to point out that R7 here is 1/7 factorial at 1. R7 at 1 is 1/7 factorial plus 1/8 factorial plus 1/9 factorial plus ... Okay? Yeah. And I would need an approximation for this. And obviously this thing is not going to be less than 1/7 factorial, which is the next term. It was less than the next term when I had an alternating series. Okay? And this particular sequence right here is going to be less than R7 of x in the appropriate interval, 1/7 factorial, right, times, oh, and yes. I'm going to have to finish this next time because I'm running late, and if I rush through this bit of the presentation, you're going to lose it. Okay, so we will complete this next time to tell you why this particular one didn't work and the alternating series approximation did end up as less than the next term. I'm looking for the maximum of the next term inside the interval of convergence. And we'll talk about how we work with that when it's not an alternating series next time. Thank you guys for your attention. Thank you guys for correcting my arithmetic and for doing the arithmetic with me as we're going along with this. Again, I'll have this up on YouTube here after my next class. Thank you all so much. Take care. Stay safe. I'll get your submissions in before Thursday. Okay, I'm stopping the recording.